Okay.
Awesome.
Okay. So.
Thanks, Mark.
Okay, so a little preface. This chapter is pretty long. I don't think we're going to have time to get all the way to the Couette flow. But the preceding sections I think are really important. So I would really recommend you go over the Couette flow, or we could continue it on Wednesday. But the Navier-Stokes and the Poiseuille flow, I think, are like the precursors to that. So that's what we're going to go over today. Okay, so a little style change. I have basically fill in the blanks just so we can go a little bit faster because I don't write really quickly while I speak. So we're going to start with looking at one-dimensional flow of viscous Newtonian fluids. So the first part, 4.5.1, is the Navier-Stokes equation in one dimension. So this means that we have a system that exists in 3 dimensions, but we're only flowing in one direction. So here, we're going to suppose we have a system of incompressible fluids. So that means, there we go. So incompressible fluids means this. Remember, this is our velocity, is 0. A Newtonian viscous liquid, that means that our viscosity does not change over time. So this is constant. We have flow in one dimension, like I just said, is still 3D. But we're going to have the x is a function of x, y, z, and t does not equal 0. V of y of all of that is going to equal 0. And v in the z direction of all of that is also going to equal 0. We're staying really general, so we're not assuming that there's a stationary flow. Things can still change in time. But we are going to take the Eulerian point of view. So that means we have a constant location over time. And so what does that imply? That implies that we have incompressibility, which is, well, that was one of the things we assumed, but this equals 0. And so how does that change our system? That means that this term, dot gradient of v. So that means this term in our Navier-Stokes equation is also going to be 0. And this is equal to. So I'm just writing this explicitly so we can see what happens to every term. Oops. Okay, so as stated before, oops. This is going to equal 0, and this is going to equal 0, and that's because of these conditions here, right? Because we have one-dimensional flow. And so, sorry, this is also 0. So that means that 0 equals Vx partial by x. times our velocity vector. Which means that Vx oops, sorry. X over X. Okay, so I'm just writing more explicitly what that means. And we can also recall that these two sections are also 0, and that's because our velocity in y is 0, and our velocity in z is 0, so of course it's not going to change like as we move through our space. And so that means that finally we can say that our gradient Vx is independent of x. So we have a constant speed in the x direction at some time. Constant. At some time. Okay, so what does that mean for our general equation of motion? So our general equation of motion is going to look like this. E over t plus okay. So recall what each of these terms are really quickly. So this first term is acceleration due to our velocity. And recall this is the Eulerian point of view. This section is acceleration due to convective forces. So that's like bulk movement. And then after that, we have our general volumetric forces. Next is our hydrostatic pressure. And lastly, we have our viscous forces from swimming. Okay, so with this condition that we have of flow in one dimension, what is our Navier-Stokes equation going to be? So we can look at it separately. We're going to look at x, and then we're going to look at y and z, because we know that y and z are going to behave the same way as each other. So in x, we're going to have this. So our speed of x. Okay, so that's what we have in X. Pretty similar to the general equation. And then in Y and in Z, things are going to simplify a lot because we're not moving in that direction. So in Y and in Z, we still have the volumetric forces and we still have pressure. So that's what we're going to be left with. And remember, we have symmetry here. So we're going to have the same thing for Y and Z. And these are going to equal 0. And the reason it equals 0 is because we don't have any velocity in that direction. And so this is going to imply that we have hydrostatic pressure. And this is the same, like we know that it implies hydrostatic pressure because we have this gradient of pressure balanced with the volumetric forces. And this is the same as something we solved before, which is the droplet on a surface. So recall. Okay. Any questions so far? No, solid. Okay. Page 1 out of 8. Let's keep going. Okay. So that means that in general, sorry. So now we've separated our system into X and then into Y and Z. And now we want to address like each of these terms. So we're going to start with the volumetric force. So we know that in general, the volumetric force they're just the forces due to gravity, right? So to make our life simple, we're going to say that our volumetric force is just gravity. And we know that gravity is constant through the volume. And so to understand more about the system, we want to basically look at this section. So what's happening in Y and Z, and this. So we want to look at our Navier-Stokes equation and simplify it by removing this volumetric force. Okay. So want to remove this. So to do that, we're going to see how our Navier-Stokes equation varies in X. So the direction that we're flowing. So we're going to take this derivative of our Navier-Stokes equation. So we're going to start by doing it in Y and Z. Okay. So, okay. So that means we're going to have this derivative. So we know that we have this equals 0 here. So that's where I'm getting that. Fy minus y. And that's of course going to be the same thing for the z direction. Okay. And so what we can do is we can change the order of the derivatives to see explicitly how does our gradient of pressure in X change, like spatially. So because we know that these forces, the volumetric force Fy and Fz, they don't change with respect to X. So those are going to be equal to 0. So this equal to 0. And so we're going to get the following. Okay. And so by changing the order of the derivatives here, we can see something about the change in pressure with respect to the direction that we're flowing. So, oops. So, okay. So, this means that our pressure gradient, where's my pen? There we go. Our pressure gradient with respect to the direction of flow does not change in y and in x. Okay. So this implies that change in p over change in x is constant in y and z. And of course, the obvious question is the change in pressure with respect to x constant in x as well? So, but is rho p by rho x constant in x dimension? Okay. Do we have any guesses so far? So right now in our system, like let's look back at what we're assuming. So we just have some incompressible fluid going in one direction, flowing in one direction. We don't have any like bounds or anything, and we're taking the Eulerian point of view. So here's where we're at. We know that our gradient of pressure in X is not varying in Y or Z, or so in the perpendicular plane to our flow. So is it constant in X? So no guesses, that's okay. We're going to look at our velocity vector. So since we defined our velocity vector Vx as a function of y, z, and t, this implies that Vx is independent of x. Okay, so when did we define that? We defined that back up here. when we said that our fluid, when our fluid is incompressible, we concluded that we have some constant speed in x as a function of t. So our velocity in x is independent of x. And so because we had that condition before, we're able to say that our velocity in x is independent of x. That's why it's not listed in these parameters. And so we can say that brings us here, right? So our velocity in x is independent of x. And so what does that imply about our Navier-Stokes equation? That means that when we do the derivative of that equation with respect to x, we should get 0, right? Because our velocity in x is not dependent on x. So let's write that out. So this implies that Navier-Stokes okay, great. And so what does that imply? That implies that we're going to take that derivative and see whether or not we're going to see if this is constant in x. So that's our goal right now. And so we're going to do that derivative. Dx over t. Okay, and so we're just going to expand this a little bit, and then we'll see which terms fall to 0. So have this density pop out, rho t Vx over given that we have this condition where Vx is independent of x, what does that mean about this term?
0.
Yeah, 0, exactly. Equals 0. Let's continue to the next one. Factor out our density. Then we're going to have volumetric force x over x minus okay. And once again, because this because this is 0. That means, of course, these two, which are the same, all three of those are going to be 0 because our velocity in x is independent of our position x. Sorry, our gradient in x. So these will fall to 0. And then we get a very nice simplification where 0 equals this. And that implies that our gradient in P for x is constant in x as well. And so that means that our gradient of pressure in x is constant in all three directions. Okay, so we did all of that, but for what? What does this mean? So this means that for a steady state flow, so steady state flow is AKA time independent. So for a time independent flow, we're going to have the following Navier-Stokes equation. So I'll have dV by dt plus our gradient of our stress tensor. So recall that this is the stress tensor. Okay, and we just said that this is time independent, so dV by dt is going to equal 0. So we have 0 equals our density times volumetric force plus gradient this. And what does this mean? This means that we're going to have, sorry, this implies that our momentum, I'm writing momentum as like a double line P, not to be confused. P, which is mass times R. Velocity is constant in space and time. Is constant in space and time. Okay, so where did I get that implication? There's a few things. So first we have to note that we're in the Eulerian point of view. So note Eulerian POV. And what does that mean? That means that we're looking at a constant location over time. So an example would be like a faucet. So if I have some faucet and I have a stream of like water coming through it, ignore the fact that like realistically, if you were to have some stream, then like the radius changes. Really just simple here. The concept is that if we are looking at the speed, velocity at like this height, then we would have some constant speed where all the particles that pass through that plane are going at that speed. And if we look at some other height, then all the particles passing through that height would be going at some speed v1 or v2. Right, so it's not to say that the particles aren't accelerating, they are, but we're not looking at the particles, we're looking at some plane that we choose to observe. So everything passing through that plane will have a set speed. Does that make sense? This part was a little confusing for me because, like, why is the momentum constant when the particles are accelerating, but it's the momentum at some space is constant. And so no matter what time we look at this space, the momentum will be the same at that point. Good. Good to go? Okay, solid. So this also means that for a low Reynolds number, this I forget what this term was called. The acceleration due to convective forces, so the bulk motion, is negligible since it's similar to parallel flow. So everything we've done so far is parallel flow. And so we're saying that at low Reynolds number, systems look like parallel flow. So this is which we just proved. We just proved that parallel flow has this condition. V equals 0. And also for low Reynolds number, we know that this viscosity is going to be equal to 0. This, I mean, we don't know this yet. It's in chapter 9, but this is Stokes' equation. And we also know for low Reynolds number, or we don't know yet because this is later, but if we have some Reynolds number that is not big, but is greater than 1, it can also look like one-dimensional flow, but what is the limit? We're not sure. So this would flow like 1D. What's the limit? Find out in chapter 8. If we get there. Okay, so that's section 4.5.1. Now we're going to move on to Couette flow. So Couette flow is when we have a system like figure 4.18a. I'm just going to erase this stuff. And so we have 2 planes that are separated by some height, and one of them is stationary, the bottom one, and then the top one is moving. And we have some constant pressure in the system. So we know that we're going to have an infinite friction between the plate and the fluid flowing through it, like only at that surface. And then what does that mean? That means that we're going to have the velocity of the fluid, like at that surface, is going to equal the speed of the plate. So velocity, again, we're flowing in x, so the velocity of x at the height y equals 0 is going to equal 0. and our velocity in x at y equals our separation height a is going to be v naught. Okay, we're assuming that we have a no pressure gradient. Sorry, was that right? No pressure gradient. So we assume that the pressure is constant. Okay, so that means that this equals 0. And that's just like what we did above. 1D flow. And we're going to assume that we're looking at a stationary system, right? We always want to look at the simplest case. So stationary means that delta V over T equals 0. And this is, of course, independent of Z, right? Because everything in Z is going to be the same as elsewhere. Okay, and so we're going to assume that it's a steady flow. That means that we have a low Reynolds number, so it's non-turbulent. And then if we have non-turbulent flow, that's like one-dimensional flow. And that means that our gradient here, dot V equals 0. And the last assumption we're going to make is that the only volumetric force is gravity. So, oops. Force volumetric is gravity, which only exists in the direction y, which is just negative g. Okay. Oh, sorry, I forgot to erase all this before. Okay, so what does that mean for our Navier-Stokes equation? So that means that our Navier-Stokes equation is going to become the following. So we have our V of t. Oops. So I always start by writing the whole thing, so I can see what disappears like explicitly. Volumetric minus pressure. Okay. So we know that from our assumptions, this is 0, this is 0. So this is what we're left with. 0 equals FV gradient pressure plus this squared V. And just like before, we're going to split it up into X and Y. And we know that Z is not pertinent here because it'll be the same. So in X, what does that mean? That means that we're going to have our Navier-Stokes equation equal the following. So Fx okay. And so here we know that our volumetric force is going to be 0 since gravity is only acting in y. And that implies that we have this equals, oops. There we go. Okay, and then we can of course just divide out the viscosity to get this equation here. And we're gonna pause that for no, sorry. Okay, we'll continue in the x direction and then we'll go back to the y. So here we have seen what the simple implications have done to the x direction. And from here, we can solve for the velocity in x as a function of our height between the planes by integrating. So we know that our conditions from before, these are our bounds where the velocity of x at the bottom is 0 and the velocity of x at the top is v naught. And so that's going to give us this function. Okay. So now let's go back to see what happens in the y direction. So in the y direction, we have 0 equals this. And once again, are we flowing in the y direction or not? So what is our Vy gonna be?
This term is 0.
Yeah, exactly. Because we're only flowing in the x direction, so this is going to be 0. And so that implies that rho g equals, oops. And isn't this familiar? Yes, it is. It is the vertical hydrostatic pressure. Basically, once again, the droplet on a surface system again. So this implies that we have a vertical hydrostatic pressure. And we don't have our variable v of x in this at all. So we know that our hydrostatic pressure does not affect our flow in the direction that we're going. Well, actually, we're only traveling in the x direction, so this doesn't affect our flow at all. Our flow Vx in y. Okay. Cool. So, now we want to look at, so we've solved what happens, how the volumetric force changes in x and y, but now we want to see what happens to the viscous friction force per unit area, right? So here we have like many planes that are moving in this direction. So we want to look at the viscous friction in each of those planes. So it's really short, so I'm not going to erase it and rewrite it. But the viscous friction F of X. So just a little explanation on the subscripts here. This is moving in the direction X. as it varies in y, right? So these are on each of those planes that are moving in the direction x as varying through the height. So this is once again our, what do you call it? Viscous, what is sigma called again? I forget.
Rest.
Pardon?
Rest tensor.
Yes, stress tensor. So our stress tensor is going to simplify to this for our flow in only x. And then we know that Vx over Vy is going to be constant, and this is just going to be the variation of, sorry, it's going to be the ratio between our velocity of the plane divided by the height difference. So we end up turning this into like the explicit like change in velocity over change in height. And so that's where we get that. Okay. And so at the end, we see that we have a constant friction between layers no matter what height we're at, because this is independent of y. Okay. Any questions on this so far? No. Okay, solid. So now we're going to continue to Poiseuille flow in a planar setting. So it was planar before. Here we had two parallel plates that are moving, but now we're going to be looking at something where we have two constant planes and we have a pressure gradient in the direction that we're flowing. So here is a little like schematic of our velocity gradient, which is just is this picture again, right? So we know we're going to have some maximal velocity the furthest away from our viscous friction, like our friction between the surfaces, right? So the further we are from the surfaces, the faster we will go. And so we know we're going to have something symmetric where our Vmax is in the middle. And then we also know that our pressure is going to, we're going to have a lower pressure in later on, and we're going to have a higher pressure at low x, right? So this is our pressure gradient now. So that means that our pressure gradient dp by dx, we're going to say it's some constant negative k, and we're going to define a characteristic length in x where you feel a pressure drop. So if we have too small an L, then we're going to feel like the pressure is the same. So we choose some characteristic length where we can feel a pressure drop. Okay, so in this system, we're also going to assume that we have a steady state flow. And so once again, that means non-turbulent. That means it's going to be like one dimension flow. So this is going to be equal to 0. And so what happens to our Navier-Stokes equation? I'm just going to really quickly erase this so we can, so we can write it together. Okay. So what happens to our Navier-Stokes equation? We're going to get a simplification that looks like this, just because of these two conditions that we had before. Okay. Any questions so far? There was like a lot of assumptions we made really quickly. Okay, so just like what we did in this system where we wanted to look at the velocity as we change in y, we're going to do the same thing again. So the structure of our solution is going to be the same as before. We're going to solve for velocity in x, so in the direction that we're flowing as varies for the height between the planes. Let me just turn this on focus. Okay. So we can solve for this by integrating over our height. So recall what our bound conditions are. So our boundary conditions, we have Vx at y equals 0 equals 0. And v of x at y equals our top plate, which is also stationary, is also going to equal 0. So that means that just by plugging in those conditions and integrating, we're going to have this 1 a minus y over 2. Okay, so this is just rearranging and integrating this equation given these bounds. Okay, and so how does k relate to our maximum velocity? So the only thing that we assumed is that we have some pressure gradient where we have a high pressure over here and a pressure drop as we move in x. And we only assumed that that's linear, okay? And we know that we'll have a high speed the furthest away we are from our bounds. So how does K, our pressure gradient, relate to Vmax? So this is known as Gaussian parallel flow. Parallel flow. And it refers to a parabolic velocity profile. So that doesn't explain why, but in general, when you say Gaussian parallel flow, this is what like the general shape it refers to. And then now we will explain why that is the case. So we know that our V max is going to exist at V of x y equals a over 2. Right, so a is a separation, a over 2 is the middle of the separation. And so by plugging that in, that condition in, we can define our maximum velocity. So that's going to be k over times a over 4 times a over 2. Voila. And of course, we can just rearrange to get k, to isolate k, and then redefine our velocity as a function of height. We'll redefine that as a function of our maximum velocity. So our k equals Vx max times 8 mu over a squared. And so our velocity in x as a function of height is going to be Vx x max times 4y minus y over a squared. And interestingly, the viscosity has disappeared. So this is not even a function of viscosity anymore. I thought that was cool. Okay. So now what do we do with that information? So we can now understand where does this shape come from? We know that this shape is in fact a parabola because it varies as a function of a squared and 1 over a squared. This one, our maximum velocity is also a function of a squared. And so we can define a flow rate Q, a fluid per unit depth. So we're going to take this picture, like this picture here, and we're going to like expand it in the Z direction. And we're going to see, okay, how much fluid is going through like a little surface with like an extrusion Z. So, okay, a sneak peek before I do. There we go. Okay, so we're going to integrate with respect to our height, right? So we want to look at the flow in a unit Z like protrusion. And we're going to integrate from minus a over 2 to a positive a over 2. It doesn't initially sound intuitive because the bounds of our picture are from y equals 0 to y equals a. But basically we're just like clipping this picture and then shifting the other one down. So that's what we're doing with that. Is everyone cool with that? Cam doesn't look convinced. Okay, Cam is convinced. Okay, so that means that we can rewrite our flow rate Q as, sorry, I'll just make sure we can see that. There we go. So we're gonna have y squared times a minus y, and we're gonna evaluate that from a over 2 to negative a over 2. And so that's going to give us our pressure gradient, a cubed over 12 times our viscosity. And recall that the K is our pressure gradient, right? And so we can rewrite this as, sorry, I'll just shift this up a little bit. So this is our change in pressure over some length, a cubed over 12 nu. So this was just discretizing. I went from like partial derivative to like a discrete drop in pressure and a discrete length over which the pressure happens. Sorry, this is just L. There we go. And so from this result, we can see that Q is proportional to A cubed for some given pressure drop over a length. So that means that our flow rate Q varies much more in X than in Y. So the flow rate, I'm gonna jump back up to that picture again. So this, like the flow rate through any like plane, like small section, is going to vary much more if we increased like the space between these two planes rather than if we looked at like a plane like further back, right? So if we compared those two, it's not going to change very much. But if we compared a system with like a really, really big separation and we looked at the same little square, then we would have more flow by a lot, by a to the cube. Okay. Okay. So now if we want to look at the average flow velocity, we can define an average flow velocity called U, where where U is Q over A. So we're now normalizing with respect to our separation. And that will give us K A cubed. Oh, maybe that should be a squared. Let me check the textbook. I might have made a little mistake there.
That's a square, yeah.
Yeah. Yes, indeed. Okay. Oops. Squared over 12 mu. And recall that K equals our max velocity times 8 mu over A squared. And so that means that our average velocity, sorry, our average flow velocity is going to be the following. So it'll be 2 Vx max over 3. Okay. So interestingly, when we divide by our separation, so when we define an average flow, it like we get a function, just like some proportionality with our maximum flow rate. And remember that in the maximum flow rate is our separation dependence. But you can say that the average flow is just 2/3 of the maximum flow for any separation. Okay, so the last part that I hope to cover today is posé in a tube. So that's 4.5.3. I will just erase some of this. But basically, the difference from this system between this one and the last one is that now we have a tube that we're flowing through, rather than before where we just had planes, like infinite planes that we're going through. So small difference. We have like friction in like friction along a cylindrical surface, and the pressure gradient is still linear. And we'll see how that changes our flow. Okay, so we're gonna suppose that we have the same system as before, but tube geometry. Here they drew it as like some holes in the tube. Uh, that's one way to think about it. I find it a little bit confusing because you could think of like things flowing in versus flowing out, but it's just we have some pressure at the beginning and some pressure at the end of this discrete length, right? So we're now flowing in the Z direction, and our system is in R, phi, and Z, and we have symmetry around phi. Okay, so what is our pressure gradient now? So our pressure gradient is, again, going to be constant. So we're going to use the same K, and we know that it's some discrete change in pressure over a separation L. That's going to be negative this constant. Yeah. And so now we're going to split the problem into two sections. We're going to look at the velocity field for the flow, and then we're going to look at the viscous friction on the viscous friction force on the walls of the tube. Okay. So just like before, we're going to look at the Navier-Stokes equation, and we're going to split it into the different directions, and we're going to see what changes in R, theta, sorry, R, phi, and Z. So in the R direction, P over R. So now I'm skipping some steps because we've done this many times. Zero equals -1 over R rho sine. So this is minus rho G sine phi. And then in Z, we get something very funky. Well, not that funky, but negative gradient P over Z velocity Z. And so we can expand this a little bit more. We know that this first term equals K, right? And then our Laplacian of the velocity in Z is going to be the following. Gradient. Okay. So, where did I get this? I got this from, well, I didn't actually expand it, right? This is still here. And this Laplacian, I just expanded because this is cylindrical coordinates, so things are going to change a little bit. We have this factor of r that comes out. And I think I forgot to write the viscosity here. There we go. Okay. Now we're good. And so what we want to look at is we want to, of course, the goal is always we want to look at the velocity profile as a function of r. So we want to isolate, we want to do separation by variables. So we want all of the r's on one side. And so let's, we can simplify this equation. So we're going to have k over u equals, I think I missed a negative sign. Yeah. Okay. And so we can solve by integration. We just hide that. So we can solve this by integrating over the radius, right? So if we can look at our picture again, I'll just put it here. Here's our picture. Whoa. Okay, there we go. So we're going to integrate over the radius of our tube. And once again, the boundary conditions are that when we are at the surface of the tube, then we're going to have a constant velocity of 0. We're going to have velocity of 0. Oh, they also note in the textbook that we were eliminating log of r at r equals 0 because it diverges, and we know that that's not what's going to happen. We're not going to get a divergence. We're going to get our maximum velocity at r equals 0, where r equals 0 is the center of the tube. So that means that our velocity z of r is going to equal a over 4 r squared minus r squared. So big R is the radius of, this is the whole radius of the tube, and little r is the one that we're integrating over. And we know that our velocity in z max is at r equals 0. So that means that our Vz max equals k over 4 mu times r squared. Big R, radius of the tube. And then so we can rewrite again our velocity in z as a function of our max velocity. So that will give us Vz max times 1 minus r squared. Okay. So given some maximum velocity, we can see how our velocity in Z changes with respect to the radius of the tube. Like, so the radius we are looking at in the tube. Okay, and so we're gonna go over the same kind of procedure as before, where we want to look at what is the flow rate going through the tube. So the flow rate going through the tube Q. So we're gonna have Q equals, I should move this down. So we're gonna integrate over the entire tube. So 0 to our velocity Z at position R times 2 pi R dr. And so that's going to give us pi over 8 R to the 4 over mu times our gradient in pressure. I mean, we could keep this either as the gradient in pressure, or we can keep it as K. It doesn't really make a difference. So we could say that that is K. Okay, and lastly, we do a funky thing where we can express Q as a function of the tube diameter and the length L. And so the goal of this is to see how the flow rate Q changes as a function of the diameter. So just like before, we looked at the flow rate as a function of the separation of the plates. Now we want to look at the flow rate as a function of the diameter of the tube. I'll just hide this. We can just do a little bit of algebra, and remember that we can change this derivative, like this partial derivative of the pressure, we can change it to be explicit. That's this here, our delta P over some length L. And recall that L is the direction, L is like a distance in the direction that we're flowing. And so when we change these parameters, remember we have R to the 4, so that means the diameter is going to be R over 2 to the power of 4. That's where we get this 128. So we're going to get this relation where we have explicitly of the diameter. And so this is called Poiseuille's law. And we know that from this equation, we have Q is proportional to, I wrote the D kind of funky because I didn't want to confuse it with the derivative D. So that's diameter to the power of 4. And similarly to the last system where we had flow between two plates, our flow rate varies more in R than in Z. So I'm just going to write that down. Flow rate varies more in R than in Z. So just like before, where our flow rate varied a lot more when we separated the plates, it's the same thing here. So when we make our diameter larger, the flow rate is going to vary like to the power of 4, rather than when we look at the flow rate across the direction that we're going, it's going to vary a lot less. So that means that, oh my gosh, I know class is over. Almost done, and I'll send you guys the last page. So this means that our Oh, wait, is class over? No, class is not over. Wait, when is class over?
2 minutes.
Okay, transverse velocity gradient is sharp with R, so it's like very steep with R. Steep in the R direction. And that means that our viscous force increases rapidly with R decrease, when R decreases. Okay, and the last part that I was gonna go over, but we're not gonna go over, is this viscous friction forces on the wall of the tube. So basically look at the forces due to friction along the tube. What does that mean? That means that we have some force in the z direction, which is like obviously in the same direction as the flow. Yeah, I don't have time to go over all of it, but I can send you this last page. And the next thing, like the last part of this chapter would be the Couette flow, which is definitely relevant. Either we can do it on Wednesday or we can do it like left as like further reading. So yeah, that's what I have.
Great, Samaya.
Yeah,
I'll leave it to you guys what you want to do for Wednesday. I have to run off to a meeting, so.
sounds good. So yeah, do you guys want to do it for Wednesday or skip
I
it?
think this cylindrical duet flow. It's gonna be, you know, kind of cookie cutter of what we've done. Just for a different system in cylindrical coordinates. I think
Yeah.
like probably get it
Yeah,
enough.
as you read over it, it's
Reading through it.
yeah.
Also, in most cases, people try to make sure that the gap thickness is really small in comparison to the radius, in which case the curvature doesn't even play a role.
Right.
Okay.
One thing I might mention, there's a first like exercise of this chapter I thought was like kind of fun to work through, which is just doing what we just did, but with coaxial cylinders. So you could
Do that for fun.
you wish.
Yeah.
On Wednesday? No. Just like
No, individually.
just whenever you want, Anya. I think I'm planning on starting the next part, or was planning on doing that Wednesday,
Sounds good.
even though I haven't heard anything yet and have no time to, but I think we'll have to make it happen. Yeah.
So that's chapter 5.
I think I'll try to carry through a good amount of that, and then next week, Marzook can maybe try to do some like of the fun application stuff of that chapter.
Do you think that's relevant? That's what I was gonna ask. How much of it?
Yeah, like I think we want to go over the like jump thing, hydraulic jump. There's this like Miranda effect. Kind of cool.
There's some